Hello everybody. This video is a quick start guide on the thermal analysis software that I have made for my master thesis. I will show where you can find the software and the documentation, how to download everything, and how to actually use the software. I will also show how to create an orbital model and a thermal model, and how to run the simulations. If you want to understand the software more fundamentally, I would highly recommend to look at the user manual that I created. I will show where to find this manual later. Let's get started. First, I'll show you how to find my master thesis and also the associated documents. So in Google, just type repository TU Delft. Go to the first entry and click here. I'd recommend to look for people because searching in this search bar is sometimes not very accurate. So type my name. And that's me. Modular Thermal Analysis. And just download the file. Alright, if you're just interested in using the code, there are two sections which might be interesting. So firstly, it will be section 3.5, which is an example case of how to create a thermal model. So I'm showing some examples here. You can see that I have some Python code and some text explaining what I'm doing. But this is just one way of defining a model. And there are some example plots here, but it's not extensive. So what I would suggest doing is to go to Appendix C instead. In this appendix, I explain much more elaborately how to use the software, what sort of syntax you should use, etc. So I start with a simplified file overview, so the files that you will get when you download the folder, what those files mean, which ones are important for you and which ones are less important. I have some diagrams of the general workflow and just a bunch of explanation here. So if you really want to dive deeper into, well, using the software as optimally as you can, then I would recommend reading this appendix. But for a beginner, it might be a bit too much information all at once. Now, when you actually want to download the software, you can go either to GitLab or GitHub. So you can see here, this reference goes to GitLab and this reference goes to GitHub. The GitLab page is an official TU Delft page and therefore is more likely to stay up to date compared to the GitHub page, which is just my private page. However, at the moment of recording this, which is October 2024, the GitLab page might not be publicly available. So just in case the GitLab is not publicly available yet, you can just look at the GitHub page here, and you can download the files anyway. So let's click on this reference here, and you will see GitLab Delphi Space Thermal Simulations, while the next reference is personal GitHub page. So let's click on both of them. For the GitLab page, this is what it looks like from my point of view. Now I am logged in as a student here, so I'm not sure exactly how this would look for you if you're not a TU Delft student. Now it brings you to the general page of Delphi Space, but if you navigate through these folders, you will eventually in the simulations folder find thermal simulations. And initially it appears that this page is empty with just a README file, but this is because it's in my personal branch here. And if you click on that, you will get all the files. For just a little bit more information, you can also go to the wiki page here. And it's just a very short file overview, similar to the README. And I have some links here as well. But in general, I would suggest to just stick to the actual repository here. Now let's go to my private GitHub page. You can see all my student projects here, but thermal analysis is the one that we care about. It essentially looks the same as the GitLab page, but at least this page is guaranteed to be public at all times. So here you can download everything here on code and then download zip. Or on GitLab, similarly, you can click on code and download it as a zip file. So once you have downloaded the zip file and open everything in PyCharm, it would look something like this. So I will quickly go over these files and show what their function is. Now, their function is also explained at the beginning of each file in this docstring here. So all files have this. However, just to explain it very briefly here, Thermalbudget.py is the main definition of the thermal models or nodal models. So this defines all the classes, which are the node, nodal model, and orbital model, which are used to create the whole simulation. So either you go to the bottom of this file and define your model here, or you create a new file and you import the classes that are defined in this file. Secondly, we have common nodal models.py, which main function is to define a number of nodal models which are very common, such as PCBs, and which can just be copy-pasted into other models. Currently, there are only two types of PCBs in this file, a PCB with 5 nodes and a PCB with 9 nodes, but future users or students might want to expand this file with whichever they think is important. The sensitivity analysis defines a number of functions that you can use to run the sensitivity analysis and also to plot the results. And you can run this analysis on your own models. So this means that you can import your model into this file, and at the bottom of this file you run all the analyses and show the plots. Funcube.py was used for my master thesis as an example for validation. So I validated this model with flight data, and in this file I defined the whole model. So this could be really useful for a new user to use this as an example, because FunCube1 is a 1U CubeSat with a number of PCBs stacked, and thereby this model could serve as an example for your own model, since they are likely to be similar. So here the model is defined with a number of PCBs, an aluminium structure, outer PCBs with solar cells, aluminium spacers in between the structure, etc. Constants.py stores a number of constants, which are used for all the computations. And each constant has an identifying number that is associated with a certain reference. So if you want to change some of these constants, which is not recommended, but if one desires to change the constants, you do not need to go somewhere inside the whole software to find this one number, but they are all stored here in this collection. Verification validation.py is mostly just used for my master thesis report and is likely not that important for the average user. But if you're interested to look at this file anyway, it contains a number of verification and validation cases with ISATAN, but also with flight data, and some plots are also compared with literature. But this is explained in more detail also in the master thesis report. Next, environment radiation.py is generally not really visited by the average user, except if you want to look at the main calculations that are behind it. But for the average user, you do not really need to use this file, because all these functions are imported into thermalbudget.py to perform the calculations. Materials.py is also not very important for the average user, because it basically acts as an API between the CSV file and the Python code. So not much needs to be changed here. Finally, testfile.py is more something for myself, since I'm a type of person that wants to be able to try out different things without messing up the important code. So maybe for you this is also important to have this test file where you can make some example models or try out some things without having to mess up your main file. But in principle this file is empty. I think we are now ready to make a thermal simulation. So as I said before, funcube.py is a good example of how to make a thermal model, but for now we will start from scratch. So let's create a new file here. New Python file, give it a name. For now I will just call it YouTube tutorial. And we will have our empty file here. We will need to start with some import statements, because currently this file is completely empty and not linked to any of these other files. I personally like to import NumPy because I use it for making NumPy arrays, but it's not strictly necessary. Next, like I just explained, the main classes for orbital models and nodal models are defined in thermalbudget.py, so we need to import those classes from here. Node, nodal model, and orbital model are classes, but this show available materials represents a function that I also generally recommend to run at the beginning of each file that you make, just for convenience, and I will show what this means later. For this example, I will also define a PCB, and I recommend to import something from the common nodal models.py, and it could be either a 5-node PCB or a 9-node PCB, but for now I think 5 nodes would be enough. This second function here, assign external heat to PCB, is needed to assign the results from the orbital model to this PCB, but this will become clear later. Like I just explained, I always recommend to start by running the show available materials command. If I now run the file, you will see that something prints in the Python console here. And this is basically a simplification of the materials database. So you can see here it shows the names of available materials, the names of available coatings, and the names of available contact interfaces. So the actual properties are not shown here, but these names are actually the handles used when you are choosing a material. So you can go into this Python console, select one of these, copy them, and then later you can paste them as a string when you want to select the material. But I will show this later. So just as a short side note here, I will show the materials database. This is a CSV file that I usually prefer to open in Excel, and it looks something like this. So this first statement is quite important, basically saying that the cells with begin materials, end materials, etc. are not to be changed. So those are these cells, and they are used by Python as a identifier. So they know when this section begins and when this section ends. So if you change this identifier, then Python cannot recognize anymore which sections they are. So that's why these are to be unchanged. Apart from that, at the top here, there is a huge reference list. And this is similar to what I did with the constants in the Python file, where I also gave reference identifiers for all the values that I found. And this is especially important if future students want to expand this database, because it needs to be traceable, of course. So the general layout of this Excel sheet is as follows. First, we will have the materials. And by material, I basically mean a solid material that has through properties. So with through properties, I mean intrinsic properties of the metal itself. So that's the density, specific heat capacity, and thermal conductivity. The density is almost never used, but if the user desires to enter a volume of a certain material instead of the mass, then this density is used to convert the volume to a mass. The specific heat capacity is multiplied by the mass to get the actual heat capacity, and the thermal conductivity is used to get the conductance through a single material. The next section defines optical coatings, or paints or surface finishes, or however you want to refer to them. But basically they just have absorptivity values, those are the first values, and emissivity values. So each optical coating is just defined with 2 parameters. And finally, the last section are the contact conductions. So this is when 2 materials are pressed together and you want to know the conductance from one material to the other. However, this is extremely dependent on the applied pressure, because if you simply press 2 materials together, you will not have a very high conductance, but if you press them together very tightly with screws, you will get a much higher conductance. So these numbers here, the heat transfer coefficients, you can see that here with the label, the heat transfer coefficients, they are very dependent on the applied pressure, and therefore it is always good to have a look maybe at this reference, see if it still makes sense, or otherwise try to find other references that fit your pressure, or maybe perform some tests so that you can actually find these values experimentally. Since the orbital calculations are normally performed before the thermal calculations, it is probably better to first define the orbital model. However, for the nodes that receive radiation, so that's usually the outside of the spacecraft, it might be more useful to define those before defining the orbital model. I'm not going to do that here, but this is more explained in the user manual in Appendix C of my master thesis report. So let's start with defining the orbit here. So to define this orbital model, we use this orbital model class from the thermal budget file. So the orbital model class takes a number of parameters, but not all of them are strictly required. When you're using an IDE such as PyCharm, you can hover the mouse over the function or class, and then it will show the documentation that I wrote. So in this case, it explains very shortly what the function or class does, and then it also shows all the parameters. And in the cases where not all parameters are required to be entered, or when there are different ways of entering the parameter, this is all explained here in this documentation. Alternatively, you could also control-click on the class or function, at least in PyCharm, and it will take you to the source code. And here you can also read all the doc strings. So let's enter some parameters for this orbital model. Let's say that the altitude is 500 kilometers. Make sure that it is entered here in meters, because also when you hover over the function, you will see the units that are used. And in most cases, I use SI units, but for angles, usually I use degrees instead of radians. I feel like radians are very unintuitive for the normal person to use. And if you'd have an inclination angle, you would never know the angle in terms of radians, but always degrees. Anyways, long tangent. So basically here the altitude needs to be entered in meters, so 500 kilometers in this case. And the next parameters is surfaces. And what the surfaces argument refers to is basically the elements of your model that receive environmental radiation. So in your spacecraft, these would be the outer panels. So if you have a small cube, this would be 6 nodes, because there are 6 outer faces of the spacecraft. And there are a few different ways of entering these surfaces, but in my opinion, the easiest way is to define the direction in terms of X, Y, and Z. And I will quickly show a diagram here on screen that shows what these directions mean. And then you can use that to define your panels. Because basically in this orbital model, you do not have any thermal parameters yet of your nodal model. But these surfaces are just directions, so basically attitude components, angles, that are used to compute the angle with respect to the sun and the earth, and thereby compute the heat fluxes. So just having those directions X, Y, Z is sufficient to fully define this orbital model. So let's say we have a CubeSat with 6 outer faces, then we can just enter X, Y, Z and all plus and minus. The next parameter that I will enter is the beta angle. I'm just putting 30 degrees here because it's the same as the FunCube model. And if you do not know the beta angle value, you can use also the right ascension of the ascending node and inclination, which are then automatically converted to the beta angle. Furthermore, we need the day in the year, which is just a number between 1 and 365. So let's say I'm going to choose something simple here. We want the 25th of January, then we can just say day is 25. Then we can add some additional information on the actual computation. So by default, one orbit is computed, which you can also see here above the cursor. This is also mentioned in the doc strings. So when you hover it here, it says what the default values are. Now, what could be nice to consider is that for most thermal simulations, it takes a few orbits to stabilize the temperatures until they are actually periodic. So I would advise to use at least 2 orbits. Next, we will assign the time step in terms of seconds. So here, let's say we just do a time step of 10 seconds. However, the next argument, the angular rates, shows that in some cases you might need a smaller time step. So let's define some angular rates, which is basically tumbling of the spacecraft. This is defined in an array with 3 elements, which are the rotations in X, Y, and Z. So let's say that it just spins around the Z-axis now. I can say, for example, it spins with 5 degrees per second around the Z-axis. And basically these values in degrees per second, they can determine what your time step would have to be. Because if you have a really quickly spinning spacecraft, you need also better time resolution to resolve all those rotations. So just to do a sanity check here, I have a time step here of 10 seconds and my Z-axis rotates at 5 degrees per second, which would mean that per time step it rotates 50 degrees, which I think is quite large. So in this case, I will lower my time step by a factor 2, let's say, and now we only have 25 degrees of rotation per time step, which I think for a thermal simulation in this case is reasonable. So now we have the orbit fully defined and we can run it, which is simply done with a compute function. And the compute function doesn't have any return arguments, but it just stores the solution within the orbital model itself. And we will extract this later. One thing which I would advise you to do is to extract the time array from this orbital model as follows. Just to very briefly explain why this time array is needed. Basically, when you are coupling the orbital model and the thermal model together, you want all the time steps to be the same. And you want the time arrays to be the same length and to have the same step size. So that's why if you use the time step of the orbital model here and use it later to define the nodal model, you are guaranteeing that the two are connected properly. And you are avoiding that your two time arrays are different, because if that's the case, you cannot run your simulation. So now that we have defined the orbital model and have computed the results, we need to connect the results to some nodes. Because now, basically the results are stored as a function of these surfaces. So we have the environmental heat fluxes throughout time for x plus, y plus, etc. But these are not yet thermal nodes. So first we need to define some thermal nodes, and then we will connect the heat fluxes that we computed for these surfaces. We will connect those to the thermal nodes that we make. Now there are multiple ways of doing this, and I will start with the easiest way, and then I will quickly show another way which might be interesting if you want to have a high fidelity model. But I will just start with the simple way. So first I need to define the 6 outer nodes that we have. So again, remember that these are basically the outer plates of the spacecraft that receive environmental radiation. So let's make it simple here and just define 6 nodes. And for this we use the node object that again we have imported from the thermal budget file. Similar to the orbital model, we can hover over the node and we will find all the information of all the parameters here. But I will just quickly show you now the most important parameters. Firstly, you should give your node a name, because the name that you give to the node will be used also within the software itself as a unique reference identifier. So whenever you are naming your nodes, you need to make sure that the names are all different. Because if you have multiple nodes defined in one nodal model, but the names are the same, the nodal model does not know which node would refer to which one, because they have the same name. So what I like to have as a sort of rule for myself is to make the name of the node the same as my variable in Python here. So if I name this x plus, it could be useful to just name the node itself also x plus. Next, we need to give it a heat capacity, so basically a mass. And you could do this manually by saying C cap is, and then some value in terms of joule per Kelvin. But in most realistic scenarios, we do not know this actual value, but what we know is the material and maybe the mass. So that's what we will do here. And for that, we're using the material database. So we start by defining a material, which needs to be a string, and this could be any of the materials that are in the material database. So again, this is why this show available materials function is useful, because I have some prints here in the Python console, which I can just copy paste into my material definition here. So let's say that this outer panel is a PCB. We just copy this over and paste this as a string into the material definition. Then we also need to give it a mass. So let's say this one is 20 grams. And again, you notice that the unit here is kilograms because most units are SI. Now we also need to have optical properties assigned, which is not always required, because if you just have a conductive node that doesn't radiate anywhere, the optical properties do not have any influence. But especially for outer nodes and nodes that use any sort of radiation or have radiative heat transfer between other nodes, we need to define these parameters. So we could say that we manually define them like that. Or alternatively, you could use the database and you say coating is a string, which could be any of these. And let's say this is solar cell mix black paint. This one is a little bit random, but for FunCube, I realized that the outside of the spacecraft was mostly solar cells, but also some black paint because the solar cells did not fully cover the PCB. So I could use this one, for example, and use that as my coating. Now I just realized that I made a, not really a mistake here, but I would say a sort of convention error. So for the outer nodes, when I'm using these surfaces X plus, Y plus, etc., it is advised that you use those exact identifiers also as the name of these nodes. So instead of saying X plus here, I could say X plus like this, because this is used in some parts of the code to try to find the outer nodes and to see to which surfaces they belong. Now this is not strictly necessary, but it is good to keep this as a sort of convention. And you just need to make sure that this is within the name. So I could also call it, for example, X plus A, or I can say PCB outer X plus, as long as this sort of identifier is in there. And that will make sure that the code will recognize it themselves. So now we have a lumped mass, which for some cases would be enough. But since we are actually receiving radiation and emitting radiation as well, we need a geometry, right? So we need a surface area and we need a direction. This is defined with two parameters, of which one is called origin and one is called geom. So for the parameter origin, we basically define where the center of the node should be. So let's say for 1U CubeSat, the outer panels are all 10 centimeters long, which means that compared to the origin, let's say 0, 0, 0, they will be 5 centimeters spaced apart from that. So basically our cube is perfectly centered around the origin. So in this case, if we have the X plus panel, this one would be 5 centimeters in the x-axis and centered around y and z. And our geometry would be 10 centimeters in both y and z directions, but 0 in the x direction. Now, why do we define this as 0 in the x direction? That's because this is purely the geometry that we define, and we basically assume that it's an infinitely thin flat plate. However, when we're defining conduction through this node, of course an infinitely small thickness would not make sense. So in that case you would manually define the perpendicular area later. But for now, just for the geometry, it is assumed that it doesn't have a thickness. Then as a very final parameter, this should be done for all nodes which are on the outside of the spacecraft. So they receive environment radiation and they also emit radiation to space. We should define this parameter outer and we should set it as true. And that basically shows that this is an outer node, so it receives environmental heat and it radiates away its own heat to space. If you forget to enter this parameter, the code will realize this and automatically assign it anyway, but I would say just put it yourself to make sure that it really works. And now in this exact same way, we basically define all the other nodes as well. Now, knowing where exactly to put these origins and the geometries might be a bit annoying to understand. So either you could look at the FunCube example that is in this FunCube file, and you can simply copy those values because that's a 1U CubeSat. So for most cases, just 10 by 10 by 10 centimeters will result in this sort of geometry. But alternatively, you can also try this out, and then later I will show you, if you run the simulation, you will get a plot that visualizes this, and you can visually check whether it makes sense. So now we have defined the outer nodes of this model, but still they're completely separate from our orbital model, right? Because we computed the orbital solution and it is stored inside the orbital model object in terms of this x plus, y plus, etc. But now we want to link those to the nodes that we just created. Now there are two ways to assign the environmental heat to these nodes. And the first way is to add this extra parameter here called Qext, which are the external heat fluxes. And it's basically a tuple with first the planetary heat, then the albedo heat, and then the solar heat in watt per meter squared. However, we're not going to enter them manually, but we will use the data that we get from our orbital model. So I can say example orbit dot get heat. So we want to couple the x plus surface here from the orbital model to our x plus node, and that is why here we just select x plus, and thereby this get heat function will return the heat fluxes for planetary albedo and solar heat of example orbit and put it into this x plus node. So we do the same for all the other nodes. And then we have assigned all the heat fluxes. Now another way in which you could do this, which is maybe a little bit easier, but in principle it doesn't really matter, is that you define all these nodes before defining the orbital model. And then instead of giving the surfaces like strings like this, you give the actual object of the node. And then you do not need to do this heat assignment step, because the compute function will automatically store the heat fluxes in the node. So just as an example, let's do it for this x plus node. We could define it before defining the orbit, then we do not do this. And instead of x plus here as a string, we just put the actual object. And now we have basically done the same as we were just doing. So it's similar, and it doesn't really matter which one you choose. Another thing that I want to show is when you have PCBs as outer surfaces. So instead of just having one node per outer surface, what if you have, for example, a PCB of 5 nodes? Then in that case, we would basically be using this make 5-node PCB function to define the PCB, and we would need this assign heat flux function to assign the computed heat from the environment to this PCB. So let's say for our x plus phase, we have 5 nodes, and we use this function to define them. Then it would look something like this. So here I'm using the make 5-node PCB function to make this x plus phase with 5 internal nodes. So this x plus is now not one single node anymore, but this is considered a nodal model. And nodes A, B, C, D, and E are all the individual nodes in this model. And again, we need to make sure that the title here contains x plus, y plus, etc. One of those, so that this function knows what we actually mean, which direction it refers to. And also in this case, we need to specify the thickness, which by default is set to 1.6 millimeters, which is standard for PCBs. And we need to define the time array as well, which is our orbit time here. And then this PCB is basically formed. Now, like I said before, it would be possible to modify these nodes all individually and assign the heat. So that would look something like this. However, it would require a lot of these statements and it becomes really ugly. So instead, I just use the function that I imported, which is the assign q external to PCB function, and it makes it really easy to do. So you just do it as follows, where basically here you enter the nodal model of this PCB. So not all those individual nodes, but just this nodal model, which intrinsically contains all these nodes. So I add it here, and then the orbit which I want to take my heat from, and that's it. And in case I have multiple of these 5-node PCB statements, so let's say I have another one, but for y plus, just I'm not going to fill this in, but just as to get an idea, you could here add this as a list, x plus, and add all of them here in one statement. So you could define these PCBs all like this, and then just one statement here is sufficient to assign all the heat fluxes to these PCBs. But in this case, we're just assuming that each outer node is just one node, like this. X plus is just one node, Y plus is one node, etc. And that makes it a lot easier. So now we can go to defining our thermal model. So part of the thermal model are already these nodes, but this is not sufficient because this is just the outside of the spacecraft. So let's just define some more nodes. I will try to keep it simple here and just make some nodes to get the overall idea. So let's actually put one PCB on the inside, which uses the same function that I just showed, which is this 5-node PCB function. So let's just call this PCB internal, I for internal. So we basically just did the same as what I showed before, where we have this PCB-I as our nodal model of the PCB, and then that consists of 5 nodes, which is the node on the inside and the nodes on the corners. But I will show this quickly on screen with a nice diagram, which shows how a PCB like this is built. And again, we are naming the title here PCB-I, which is the name of the whole PCB nodal model, but by default this function makes the names of the individual nodes to PCB-IA, PCB-IB, PCB-IC. So if I would print, for example, print PCB-I dot title, I would get PCB-I because that's the title of the nodal model. But if I would print the name of, for example, this node, I would get PCB-IA because it's automatically assigned. And an additional thing that I did here is to define a power, which is just an internal power on the center node of the PCB in watts. And in this case, we do not need to define the outer statement, such as here, because this PCB is on the inside, so it doesn't receive any environmental radiation. Now, just to get an idea, let's add one more node, which would be a battery. So I'm going to add a battery to this nodal model. So I'm going to say PCB-I bat for battery, and I'm going to make it into a node. And for now, let's just say, let's see what materials we have available here. I don't have the actual material of a battery because it's more complicated. But for now, let's just assume copper. Assign a coating. Well, in this case, it doesn't really matter because I'm not going to make this node radiative. It's not going to radiate to other nodes, but just as a good measure, let's just always assign the optical properties. So let's just say that it's black paint, which you can also find here. Give it a mass and give it an origin. And one thing which you can notice is that for all the previous nodes, I gave it an origin and a geometry. So the origin is the center of the node, and then the geometry is the actual shape that the flat plate has, because I assume it's a flat plate. However, for this battery, well, it's obviously not a flat plate. And it also doesn't have any radiation, right? So I'm going to assume that it doesn't radiate between other nodes. So a geometry is actually not necessary. So in this case, I just give it an origin so that it will show up in the 3D plot that I will show later. And thereby I will be able to know, okay, it's roughly here. But in principle, this origin statement doesn't do anything now because it's not a radiative node. But for good measure, you can always include an origin to keep track of your nodes a bit more easily with a 3D plot. Okay, let's say that that's enough for our entire model. I'm completely neglecting the whole structure and spacers and anything that will be inside this satellite, but for now I think this is enough to get the point across. So we have all our individual nodes, but they are not yet connected. So we are going to connect them and combine them into a single nodal model. So as you can see here with our import statements, we have used the node class, we have used the orbital model, but we have not yet used the nodal model. So just these individual nodes that we created, they're not yet a nodal model. Well, except this PCBi, I guess, which is a nodal model. So we all have a lot of separate nodes here, but they are not yet connected to each other, except the nodes here in the PCB, which automatically are connected to each other within this PCB. That's what this function is for. But the PCB itself is not yet connected to any other parts of the spacecraft. So let's first define our nodal model. We're using the nodal model class for this, which again, we imported from Thermal Budget. Give it a title. I need to give it a time array. And I can specify whether I want it in degrees Celsius or Kelvin. If I say Celsius is false, it's going to be in Kelvin. And if I don't say anything, the default parameter Celsius is true. So if you just do it like this, it will always be in degrees Celsius. Now, the reason that I defined this time parameter here is what I explained before, where our orbital model has this one time array, which is assigned based on your time step that you make and the number of orbits that you want. So that's this time array. And I want it to be the same for my nodal model, because otherwise they're not compatible with each other. So that's why I say here, t is t. And this t refers to this one. Now, it is also possible to create a nodal model without this time array. However, as you can imagine, now I cannot solve the model. So I can only create the model in this case, but any time-related parameters, such as a varying internal power or external heat fluxes, they will not be compatible because I don't have a time array here to assign everything to. And then I also cannot solve the model. So that's why I recommend to always first make this orbital model, set the time array here, and then use that as an input for the nodal model. And now that we have the nodal model, we can add all the nodes to it. And this could either be a single node. So for example, I could say add PCBi bat, and it would just add this one node. I could also say I want to add a nodal model to it. So I could add the entire nodal model PCBi, because just to remind you, this is the nodal model that represents this PCB with these nodes. And with this functionality, by adding a nodal model to a nodal model, you create this hierarchical structure, which basically makes this software modular. And you can have as many sub-nodal models as you want. So I could add this nodal model to another nodal model, etc., etc. But now we just want to add everything at once. So we make a list here and we add all these components. So we say x plus y plus etc. For the PCB, we can just say, okay, add this nodal model. And because this nodal model contains all these nodes, we don't need to enter these individually anymore. So we can just say add PCBi, and that's enough. And then finally we add the battery. So now all the nodes are added to this nodal model, but they are not yet connected to each other. So we need to connect them. I'm not going to do a very realistic connection now, but let's just do this as an example. So first I want to conductively connect all these outer panels. So let's say that they're touching at their edges, and I'm just going to connect them that way. Just as an example, you can connect two nodes to each other, for example like this, where you put the first node here as node 1, and then you put the second node, and then you put some conductance value. But another way to connect the nodes is to do multiple at once, which in some cases might save some lines. So here this first node will always just be one node, but the second one you can replace by a list, and then you can add multiple nodes. So let's say x plus is connected to y plus, but also y min. Then now you're connecting x plus with y plus and x plus with y min with this same value. And if you want to give them a different value, you could do this, for example. You could put them into a list, and now x plus and y plus is connected with 1 watt per Kelvin, and X plus and Y min is connected with 5 watt per Kelvin. So for now, I'm just going to assume that all these connections are symmetric. So in this case, X plus, I can connect it to Y plus, Y min, and Z plus, and Z min. And there are a few different ways to define this connection. So, well, firstly, it could be a radiative connection. And in that case, I can just say rod is true. And then the view factors between these nodes are automatically calculated. But this is only possible if these nodes have geometry defined and if they comply with a number of rules. And basically the rules that they need to comply to is that they are either perfectly parallel to each other or they're perfectly perpendicular to each other. And those assumptions are used to calculate these view factors. But more on this can also be found in Appendix C of the master thesis. For now, let's say that they are not radiatively connected, and by default it is set to false, so I don't need to do anything here. And I want to make a conductive connection. So one method is what I already showed you before. It's where I just define the conductance in watt per Kelvin manually. So I can say, for example, 2. And now X plus is connected to Y plus, Y min, Z plus, Z min with 2 watts per Kelvin. But a value like this is not always available because this usually comes from either a lot of previous data or thermal tests or stuff like that. But we can also use the material database for this to just get some estimations, and I don't need to know the actual value in watt per Kelvin. Conduction could be either through conduction, which is through a single material, or a contact conduction, which is when two materials are pressed together. And in this case, because we have different PCBs, these are all different from each other, they're a contact connection. So in this case, let's hover over connect. We need contact obj, so the contact object. And we can check that from the material database here. So there are currently not a lot of contact interfaces present in this database because it's really difficult to find these numbers. But let's say that we thermally connect them with graphite. It doesn't really make sense because there's no real reason to do this, but let's say that it's the case here. Then I copy that string and I paste it here, and now my contact object is this graphite. And the only other thing that I need to do is to define the surface area. So in this case, it's the contact area between the two surfaces. I'm just going to put a random value here, let's say 0.0001. Now, if you don't want to use a material database for this, instead of this contact object, you can also directly define the heat transfer coefficient, which is just defined as h, but I named it h contact to make it more clear that this is related to a contact connection. So in this case, for example, it could be 1000, and this is in watt per meter squared Kelvin. Now let's say hypothetically that instead of a contact connection, I would want to make a through connection here. Again, in this case it doesn't make sense because I have different PCBs connected to each other, but let's just assume that now they're all just one big PCB and I just have different nodes in this PCB. In this case, it's actually quite simple because the material that is assigned with the material database, so for example here these nodes, they are assigned the material PCB. In the database, this actually has the conductivity defined as a parameter. So when you assign a material like this, you have this parameter already available. So I don't need to use a material database here like this, but I just define, again, well, it's not really a contact area, but it's a cross-sectional area here. I need to define it again like that. And I need one more parameter, which is the distance between the nodes. So in this case, let's say that they are 5 centimeters apart, just as an example. And then this is sufficient. Now, the way that this connect function knows the material is by checking the material of this node and checking the material of these nodes. And I can only use this through connection if they are the same material. Because if there will be a different material, well, it's not a through connection, but it will be a contact connection, for example. So I can only do it like this if these have the exact same material assigned. and let's say you have some weird scenario, then instead of the material, you can overwrite the value just by also giving a K through value, let's say 100 watt per meter Kelvin. And now this material assignment is not an issue because the connection is fully defined with these parameters. And again, instead of all this, you could also just say Ccon is some value in watt per Kelvin. Okay, so we have connected this X plus node to these other nodes, but if we want all the outer panels connected to each other, we need to define just a few more. So I'm going to do that now. So now the outer panels are connected to each other conductively. Now we want to also connect this inner PCB to the outer PCBs. So just for simplicity, let's say that it's connected to the Z- and the Z+ panels. So it's just a vertical stack essentially, and I give it some random value. In this case, I cannot actually enter PCBI because remember, this is the nodal model of this PCB. But if I want to connect something, it needs to be a node and not a nodal model. So in this case, since node A is always the center node, I'm going to connect it to the center node. And I'm connecting the center node of this PCB to Z+ and Z-. Again, these values are just random, but it's just to get an idea. In reality, through the corners of all the PCBs, you usually have a few rods. And those rods are the parts that conductively connect everything to each other. So instead of using this center node to connect the PCBs in the stack, you would say, okay, I'm going to connect the corner nodes. For example, corner B, I connect it to Z+ B and Z- B, and then you would do that for all the corners. So that's a more realistic scenario of how you would conductively define them. I will also add rod is true, which basically allows the PCB to radiate vertically in the stack. So it radiates from between the Z-, C+, and PCB panels. Just as a final step, let's connect the battery to the PCB which it's on. I'm just going to make this area larger because probably the battery is better connected to the PCB, but again, these values are kind of random. And for now, we assume that this defines our model. So we have a stack of just one PCB in the middle, and we have all the outer panels. Now, I will mention one more thing, which I didn't do here at all, but it is possible to modify a node after you've already created it. So if you just want to modify a node, I could say here, for example, x+.modify, and you can select any sort of input parameter that you previously had and change it with a new value. And that will then change the node. However, if a node is already connected to a nodal model, you also want the nodal model to adapt with the change that you make. Let's say that I want to change something in this X+ node. Ideally, I would change it here at the source, right? So let's say the mass, I would make it 0.5, right? And that's how I can change it. If that's not possible, I could do it here, for example, x+.modify, and I say mass new is 0.5, and now it's changed. However, here at the end of the code, I already have this node added to the nodal model. So let's say that I have this nodal model present, and I want to change it here in this part of the code. If I now say x+.modify and I change this value, yes, this x+ node will change, but the nodal model, this example nodal model, does not know that this change is happening. So I need to make sure that I change it within this nodal model. So instead of saying x+.modify, I say example nodal model.modify node, where you select the node that you want to modify. So you say node mod is, I can give the object here x+, or I can give the string identifier, so in this case x+, both work. And then you can say mass new is 0.5. And that changes the object x+, but it also makes sure that this nodal model changes along with it. But anyhow, we basically have our model finished now, and it's ready to solve the model and to show some plots. Solving the model is really easy. You just use the .solve function, and it doesn't really require any input parameters. Now you can hover over it and see that there are some options available. For example, you can change the numerical solver, you can add an initial temperature, or you can add some other parameters. Just for those interested, if I add a T0, it's going to set all the nodes to this temperature. But if I have some very specific initial condition, you might want to define the initial temperature of all the nodes individually. If no initial temperatures are given, the solver will perform a steady state analysis based on the average power throughout the whole orbit. So if you have a bunch of solar heat, internal heat, all those things, based on the average power of the whole orbit, it will compute a steady state and then use those results as an initial condition. Anyhow, we have now solved the model and we can plot the results. So, well, you can manually extract the data, for example, by using the .t parameter. So this is the property of this example nodal model, and these are just all the temperatures. And in the appendix of my master thesis, there's a lot explained about this. However, in most cases, it's probably sufficient to just use the show plots function. So I will say example nodal model dot show plots, and just by doing this, it's a principle enough, and I can run this code and I will generate some plots. I just realized that I made a small error here, because this PCBi is actually a nodal model and not a node. So when you are connecting nodes within a nodal model, you need to make sure that you reference the actual node. So here I want to connect it with PCBi-A, so I need to type A here, because otherwise it does not know which node within this nodal model to connect to. And now we can run the model and see some plots. Let's first have a look at the console here. So it's printing a bunch of things. So again, first we have this material database properties. And then it's printing the progress of the orbital analysis. And then here, this is talking about the transient analysis. So first, we are performing a steady state, which is based on the average heat fluxes throughout the whole orbit, what I just explained. And then we're doing the transient analysis, and it's finished here. And associated with this show plots function, I also get a model tree here. So you can see that our main nodal model is this example nodal model. We have some nodes here, and we have a battery here. And we can also see that this PCBi is a nodal model with nodes within itself. So this is the sort of hierarchy that you can see. Now let's have a look at some plots. So the first plot that we see here is this geometry plot, where you can see all the types of nodes that we have entered and also their connections. So the black lines show the geometry of each node. So let's say here you can see Y minus has a center here. So this is the origin that you define. So it has its origin here, and its geometry is defined as follows. And then with all the other ones, it makes this cube. And you can also see here that this PCBi-A is the internal PCB that we defined. And you can see here that this is this plate in the middle. Now you can also see all these red lines in between, and those are conductive connections, while the green dotted lines are radiative. So for example here you can see vertically you have Z minus connected to PCBi-A connected to Z plus, both conductively and radiatively. Now there's another thing that you might be able to see. It's a bit difficult in a plot like this because there's so much going on. I will show a solution for that later. But you can see here, if you look at this PCBi, PCBi-A, B, C, D, E, you can see that they are all connected in this sort of X shape. And that resembles the diagram that I showed before, which is basically the default way in which a PCB is defined when you use the make 5-node PCB function. But there is a small thing that I want to note here. If you have a really big model, it will be impossible to read this plot because there's too much going on. So I will now show a quick solution for this, where you can, instead of plotting every node, select which node you actually want to plot. So going back to our code here, in the showPlots function, you have the optional parameter called which nodes. And with this parameter, you enter a list like this with the nodes that you want to show. So you could use either the objects for this. So I could say, for example, x plus, right, which is the object of the node, or I could use the strings as their identifiers. And I would recommend using the strings because if you import a nodal model from some other file, you don't actually have the actual object, but then you would just refer to these strings. So I'll just use the strings. So I can say, for example, let's say that I just want to see the PCB. So I'm going to say PCB IA and all the other ones. And let's see what that looks like when we run it. And now, as you can see, the plot is much more readable because with my which nodes argument, I selected which nodes are printed. So it shows the nodes themselves and the connections between them, but it does not show any other connections that these nodes might have. So for example, our PCB IA is connected to Z plus and Z minus, but because I did not select those with my which nodes argument, those connections are currently not shown. And what's also good to know is that this which node argument does not only simplify this plot, but it simplifies all the other plots as well. And it basically follows the same principle where it just shows the nodes that you selected. And that makes the temperature plots, for example, also much more readable. So for now, let's just plot everything again. I'm going to remove these which nodes. Just going to put them in a comment here in case I want to use them again. So now let's just show everything again and let's go to the other plots that are shown. So the next plot that is shown is the environmental heat flux plot. And in this case it looks really crazy, but this is because, I don't know if you remember, but we assigned a rotational rate to the z-axis. So that means that our spacecraft is actually spinning at, I think it was 5 degrees per second. So if I zoom in on this, for example here, you can see that you have all these oscillations in environmental heat power. So actually it makes a lot of sense here. It makes the plot a bit difficult to read. So I think just for your ease now, I will change the angular rates to 0 and let's revisit this plot again. And now the plot looks like this. So it's basically the same plot as before, but now we're not rotating the spacecraft really quickly. So it's just following the curvature of the Earth. So basically the coordinate system is with respect to the velocity vector. And in this case, basically the z plus is the velocity vector. So on the x-axis you have time in seconds. On the y-axis you have the power in watts into each node. And then here you can see all the nodes. It's recommended to use the which nodes argument to select just a few so that it's easier to read this plot. So you can see x plus, it receives from the Earth x amount of watts, and from the albedo x amount of watts, for the sunlight x amount of watts. And if any internal power of a node is also defined, for example for our internal PCB, remember that we defined the power, it will show up here as pint. Now looking at the next plot, this is probably the most important plot of all of them, which are all the temperatures. So again on the x-axis you have the time, and then on the y-axis you have the temperature. And it's showing here the temperatures of all the nodes. So if I zoom in here, you can see all the lines individually. Now this is just an example simulation here. You can see the general behavior here. When it's in sunlight it heats up, and then here it obviously hits the eclipse. So it's behind the Earth, goes down, and then it heats up again. And because we selected 2 orbits, right, there was a manual input parameter, we get 2 orbits here. So let's go to the next plot, which as you can see has on the x-axis time again, and on the y-axis it now says conductive power from node I to J. So now we're actually looking at the heat flow between all the nodes. Now, because we are still showing all the nodes, it looks like a crazy plot and there are way too many lines. But just to get a general understanding of what this plot means, we have nodes and then number to number. Again, these numbers are automatically generated, and generally I would just refer to these names on the right here. So you can say the heat flux from, well, this center node from the PCB to one of the corner nodes is, and then it refers to one of these lines. And the very final plot here is similar to the previous one, but instead of conductive power, we have radiative power between nodes. And because we only have two radiative connections in this model, you can see that there are only two lines between the inner PCB and Z plus and Z minus. And there you can see here the power in watts. Okay, so that's basically the entire thermal simulation code. And I showed you how to make a thermal model and how to solve the model and how to show some results. But there is one last thing which you can do to this model, and that's the sensitivity analysis. And basically what the sensitivity analysis does is that it varies the input parameter that you choose by a certain percentage, and then it shows the result of that. So just to keep it easy, what I would do here is go to this sensitivity analysis file and import the model that we just made from the file that we just created. So we want to import our nodal model and our orbital model. So we have example orbit and example nodal model. So here we say, and now we just go to the bottom of this file, and here we can do our sensitivity analysis. Now, what I show here is all commented out, and these are some examples from the FunCube model. So basically you could use these examples and just copy paste them and then apply them on your own model. So let's say I want to see the effect of changing the day in the year. So here you can see day. So this is the parameter that I need to change. So I'm going to say run variable. I'm going to copy it here, just down here. This plot.show function should always be available, by the way. It depends a bit on your IDE, but in PyCharm it should be available because otherwise it will not show the plots. So let's go here. And we need to run our variable first. So the first command that we would have is run variable. And then the second command that we would have is plot variable. And now we need to select our nodal model here. So we have example nodal model and we have example orbit. And let's check these other input parameters. So it's a day. The values that we have, well, these are just a few values throughout the year. Overwrite is a boolean which you can set to true if you want your files in the folder that it's saved in to be overwritten every time. So let's say I now make a run and then I want to run it again. If I have overwrite as true, it will replace the old files that have the same name. So you need to be a little bit careful with it because it might happen that you accidentally overwrite old files that you still wanted to use. So by setting overwrite to false, it will make sure that it doesn't overwrite the old ones and instead just nothing will happen. This is also nice if you want to save some computational time. Let's say I run this and then I add here day 360. Now by setting overwrite to false, it will skip all of these first ones because they're already there, and it will only run this last one because I just added it. And then you need to define the folders in which it's stored. There is by default a folder which is called sensitivity analysis. So you can see when I hover over run variable, it will say here folder is by default sensitivity analysis. So if I want to change this folder, I can just say folder is and then some manually defined one. But I think it's nice to just keep it by default sensitivity analysis. And then if I want to have it in some subfolders, so some folders inside this sensitivity analysis, I can define them here. Now we will have a folder sensitivity analysis. In that is a folder, well, FunCube1 here, but let's now say, so we have our sensitivity analysis folder. Then we have a folder example YouTube, and then we have a folder example day. It would also be possible to just do this, for example, or to add run 1, and you can define as many subfolders as you want. And then when I choose plot variable, I want to make sure that I choose the same path, the same destination here. And now it is importing the correct file. So for this plot variable function, there's one more parameter, which is which node, and it is a bit similar to the which nodes argument that we saw before, but it's also a bit different. Because if you remember here, which nodes in this show plot, you can select as many as you want, and those will show in the plots. However, for this sensitivity analysis, it's not called which nodes, plural, but it's which node, singular form, so you can only select one node, and this will make sense as soon as I show the plots. I'm just going to select the x plus node, so we just called that x plus. And now we can run this, and it will first run all the variables and then plot them. And when it's running these variables, it will store them in this folder as Python pickle files. And what's stored is basically the nodal model. So all these computations are performed here. In the pickle file, the actual object is stored. And when I'm plotting it, I'm reading this object and extracting all the data and then plotting it. But therefore, if you run this once, then after that you can comment it out and just only use this plot variable function because the data is already available and you can just read it with this function. But for now, let's run this and see what we get. Yeah, this is, I forgot about this. This is one thing that might happen. Because I'm importing here at the beginning of sensitivity analysis, I say from YouTube tutorial, import these functions. By default, at least in PyCharm here, it runs this YouTube tutorial function. And because I have here show plots, it will show the plots. So that's what you see. Oh, it's calculating it here. So I first need to manually close all the plots. I will do it now. And then as soon as those plots are closed, here it will continue with the sensitivity analysis. So now you can see it's running all the cases for the analysis. Now what I would just recommend is that you just go here and then comment out the show plots. And you can actually also comment out the solve function, because with this run variable, it's going to solve them anyway. So let's look at the results. The first plot that we get here shows the difference in temperatures when you change the input parameter. So in this case, we have set the day to 1, 50, 100, etc. And then you get the minimum, mean, and maximum temperatures of the entire simulation. Now, the mean temperature is the mean temperature of all the nodes in your model. The minimum temperature is the coldest temperature of the entire model of all the nodes throughout the whole orbit. So if there's one node that for one time step in the orbit is really cold, then that is your minimum reading, and the same holds for the maximum temperature. Now, you can see here that in the days near January, it's hotter, and in the days near July, it's colder, which makes sense because the Earth is farther away in July compared to January. And another plot which is associated to the previous plot is this one, where once again it shows for different input variables what the results are, but instead of showing the minimum, mean, and maximum temperatures of the whole model throughout the whole orbit, you get actually time varying data. So now on the x-axis we have time again, and on y-axis it's just temperature, but we now see what happens to the temperature throughout the whole orbit. So this gives a little bit more data than the other one. However, because we might have a lot of nodes in the model, we have this which node argument, which I talked about, and that basically selects which node is shown in this plot. So here we select x plus, and therefore we see only the temperatures here of x plus. So here you can clearly see that if we zoom in here, for example, we can see, okay, on day 1 and day 350, that's basically the hottest here. And then you can see as you approach July, it will become colder. And then here, when you go more towards the December months again, it will become a bit warmer again. There's also a similar plot for the solar heat. So this is the solar heat in watts. And you can see that for varying this input parameter, how it changes the input on this node. If you select a node here that is on the inside of the spacecraft, that node doesn't receive any solar radiation at all, and therefore it will just show as a straight line of 0 here. We have a similar plot here also for the albedo heat, which in this case, well, is so small it's basically 0. But that would change if you would change this to node X minus, because that one's pointing at the Earth, so you will see a larger change happening instead of just this, well, basically 0 value. And then as a final plot, we also have the Earth infrared heat, which in this case is just one line, because when you change the day in the year, it changes the Sun-Earth distance, but it just doesn't change the altitude or anything. So nothing changes with respect to the planetary heat from Earth. So basically this one is constant, and you can see, similar to the albedo, because this X plus is pointing away from the Earth, it's basically 0. So it was just constant here, but that might change if you change the node here. Now, one more thing that I want to explain here. So just the example parameter here that I chose, day, is entered just in its actual value here. So this number that you get, also the number that you see in the graphs, that's the actual day in the year. However, when you use other parameters, for example, absorptivity, let me set this up real quick. I'm going to run the simulation again. And basically there's a difference here, because for the absorptivity and almost all the other parameters, setting the actual value doesn't really make sense. Because if I have one node which has an absorptivity of 0.8 and the other one has an absorptivity of 0.6, for example, they are not the same. So in the sensitivity analysis, I cannot change their value by just typing the number here, but I can only change them relatively. So I can change their percentage. So that's for most other parameters. And if you want to be sure, you can hover over this function and it will say here to which parameters it applies. So you can read the documentation on that. So these are multiplication factors. So this 1.0, that's our baseline, where the absorptivity is just the same as in our model. And here we multiply by 1.25, 1.5, etc. And finally, I want to see which node I'm plotting. PCB2BAT doesn't actually exist in my model. So I need to select another node, for example, X plus. So I will run the plots right now. I did a stupid thing. Here I still have the folder set to example day. So now it shows all the values of the day analysis here, because it's the same folder, and here. So always be careful with copy pasting. A lot of mistakes happen that way, as you can see. So I want to say example ups in this case. So let's do it again. So, well, I already showed you all these plots before, but I previously showed you for the day in the year. And in that case, on the x-axis, it was the actual value of the parameter. So it was the day in the year, 1, 50, 100, 150, etc. But in this case, because like I explained before, for a lot of parameters such as absorptivity, emissivity, heat capacity, all those parameters, it's a multiplication factor. So in that case, it will mention it here on the x-axis, and your 1.0 will be your baseline. That's just the normal model by itself. And then as you apply this multiplication factor to your input parameter, that's how it changes. So just make sure to read this X label properly and realize that these are not actual values, but multiplication factors in this case. And that also holds for all the other plots. So, well, here we have the plot which shows the temperature versus time. So now we don't have it on the x-axis, but we have here in this legend the multiplication factor. So as you can see, we have the absorptivity alpha here, And you can see that these numbers are 1 times alpha, 0.75 times alpha. So that highlights the fact that this is not an actual value, but this is the multiplication factor. So well, that will be it for this quick tutorial. I'm afraid that it wasn't as quick as I hoped, but I have just highlighted the most important things for using this software as a general user, and not really from the perspective of someone who wants to know all the details about the code itself or maybe even change it. Now, if you're interested in more details on this, read my entire master thesis if you want. But if you just care about the user experience side of it, you can read some more details also in Appendix C of the master thesis, which I explained before. And I will put some links in the description here. And you can also contact me by going to my LinkedIn page, where you can send me a message. You can leave a comment here below with any questions that you might have. And just in case you are interested in updating this model or changing anything about it or improving the material database, anything, let me know. I'll be very interested to hear your opinions and talk with TU Delft as well to see if maybe they have a project for you related to this. So thank you for watching and see you later.